Okay, for this video, this is about thermodynamics. It's going to be the first of 3 videos, and we're going to cover the first 2 pages of your notes. So we're going to use this handout, the 1.3.3, excuse me, to define a few things and get the basics about thermodynamics. So we are already slightly familiar with thermodynamics. If you rub your hands together, you know that they get warm, and the heat that you're feeling is called thermal energy. And the thermal energy is coming from the energy that you're putting in, which is causing friction. So your muscles are expending some energy to rub your hands together, and then the friction is creating thermal energy. So thermodynamics is the study of the effects of how work, heat, and energy flow in a system. So it's specifically the movement of thermal energy. So we use the study of thermodynamics to help us understand lots of different systems, how energy and heat move in and out of systems. So some examples would be like a nuclear power plant. There's a large amount of heat generated inside of a nuclear power plant, and we use that heat to generate electricity, but that heat has to be managed. It's got to go from one place to another. Inside your home, you have a furnace, and your furnace has some sort of a fuel source, and we're using that energy to spread energy around your house to make it warmer. But again, that's a flow of energy from one place to another. So on your notes, we define thermodynamics. I gave you 2 examples of thermodynamic systems. You should be able to come up with a third one. So now we're going to define thermal energy and temperature, which are similar but not the same. So thermal energy is kinetic energy in transit from one object to another due to a temperature difference. So when you touch something that's hot or touch something that's cold, it's energy moving from one place to another. So thermal energy is specifically talking about the transfer of energy from one thing to another, and that's measured in joules. Temperature is a little bit different. Temperature doesn't necessarily have to have a transfer of energy. It's just measuring the average kinetic energy of one particular spot. So I've got 2 tanks down here that are connected to each other. The thermometer in this one is measuring the average kinetic energy in this tank, and thermometer 2 is measuring the kinetic energy in this tank. So we have 2 different temperatures, but we have thermal energy is being transferred from the hot tank to the cold tank. So this arrow is showing the direction of our thermal energy. We have a couple different temperature scales. We have Celsius, Fahrenheit, and Kelvin. So all of these measure the motion of particles. Celsius is based on the freezing point and the boiling point of water. So the freezing point is 0 degrees, the boiling point is 100. Fahrenheit is 32 degrees for the freezing point of water and 212 degrees. And then Kelvin is has the same increments as Celsius, but has a different starting point. And Lord Kelvin wanted a temperature scale that had no negative numbers, so he was able to determine what absolute 0 actually was, and made that the lowest possible temperature of a scale. So everything is compared to that. So absolute 0 in Celsius is negative 273 degrees. So if we want to transfer one temperature to another, we can use these 4 equations. So this is Kelvin to degrees Celsius. There's a 4th temperature scale called Rankine, which is basically the Fahrenheit scale but with no negative numbers. So it's kind of like Kelvins, but with the Fahrenheit increments. So if I wanted to go to Rankine to Fahrenheit, I would use this equation. Fahrenheit to Celsius, you could use this one. And then this is basically the same equation, just rearranged for Celsius. So if you had Fahrenheit and you wanted to go to Celsius, you could use this one. Or you could just rearrange this one. So here's an example of converting 1 degree Kelvin into Fahrenheit. So I think that doesn't need much explanation, so I'll move on. The next big thing on our note sheet, so we defined thermal energy, temperature, we filled out our different temperature scales. We know what absolute zero is. Absolute zero is the coldest possible temperature, and as we saw in the animation, once you get to absolute zero, the particles stop moving completely. They just, since we're measuring the average kinetic energy, if there is no kinetic energy, then the temperature is zero. Okay, so now we're going to define thermal equilibrium and a couple of the laws of thermodynamics. Let me get to the right one here. Okay, so thermoequilibrium is when we have two different objects that are connected or touching each other, and they reach the same temperature. So the average kinetic energy of the particles here is equal to the average kinetic energy of the particles here. Equilibrium is another word for balance. So if this one started off really hot and this one started off really cold, and we mix them, once they become the same temperature, then they are at thermal equilibrium. Because we can do work with the energy moving from one object to another, once equilibrium is reached, then we can no longer do work between the two. And then we have something called the zeroth law of thermodynamics, which is kind of unnecessary, but basically it's saying if we have two objects that are in equilibrium and the second object is in equilibrium with the third object, then that one is in equilibrium with the first object. But that's what it is. Okay, so ways that energy can move from one place to another. We have convection, conduction, and radiation. So we're going to spend some time talking about convection and conduction, and we're going to mostly skip radiation for now. No type of energy transfer is 100% efficient, so 100% efficiency is not attainable, and all of these processes are irreversible, meaning they can't go back the way that they came. Okay, so the first law of thermodynamics is that energy is conserved, or the law of conservation. Energy applies to a thermal system. So if we have two different energy systems, if energy is transferred from one to another, it's the same amount of energy. Energy can't be created or destroyed. So energy can change form and can change location, but the total amount of energy stays the same. And then the second part of this law is that thermal energy can be increased within a system by adding energy, by adding heat. But to do that, you're performing work on the system. So we'll go through an example of that in just a second. So essentially this is, to put it simply, energy can't be created or destroyed. That would be the simplest way of putting the first law of thermodynamics. So here's an example. We're using a bike pump. So if we pump the handle, what is going to happen? So we are applying mechanical energy to our system. The mechanical energy is converted into thermal energy as you push the handle up and down. So you're performing work on the system. And the piston is compressing air. So it's creating heat in a couple different ways. There's friction, and then there's also temperature increase because of the pressure that you're creating. So the total increase in internal energy of the system is equal to the energy that we put in. So this pump handle, the more we use it, the warmer it's going to get. But that energy just didn't appear out of nowhere. It came from the mechanical energy that was put into the system. Okay, the second law of thermodynamics is the first part of it's pretty simple, and that's that energy flows from hot stuff to cold stuff. So when you touch frozen pizza, energy is going from your hand into the pizza. And then if you touch a hot pizza, it's going from the pizza into your hand. So energy is always flowing from where it's hot to where it's not. The second part of the second law is a little more confusing. It has to do with this word called entropy. And entropy is a way to measure how disordered something is, so how orderly or not ordered the particles are. Or another way to describe it is how evenly heat is distributed within a system. So because heat is related to the movement of the particles, entropy can be related to how fast those particles are moving. So the second law of thermodynamics is that a system usually goes on its own from ordered to more disordered. And generally, our world is always increasing entropy. It's always becoming more disordered. And the reason for that is if, for example, your room was really disordered and you spent some time to reorder it and put everything in its place, you would actually be making the universe more disordered because your body's expending energy. It's using ATP. It's using chemicals to make your body put things back to where they belong. So you're actually causing more disorder than if you had just left things where they were. I'm just going to quickly talk about how energy can transfer. Convection is something that we covered a lot in 9th grade. So a lava lamp, the inside of the Earth, our atmosphere, all use convection. It's essentially hot things rise and cool things fall. Conduction is essentially energy being transferred by things that are touching. So if you have a hot soup bowl, it's going to make the spoon and the bowl warm because energy from the soup is being transferred into things that it's touching. And this is the end of this video. I'll do another video to help us understand this equation for thermodynamics.